Today we're going to talk about discrete probability. Now, before continuing, we should note the difference between the two different types of probability. We have discrete, which is what we've learned up until now, and there's this new type called continuous. Now, continuous we haven't actually covered yet up until Year 12 methods. Everything that you've learned in probability up until now is discrete. They just don't say that when you learn it because it's kind of just the normal. So everything you've learned up until now is discrete, and then we'll introduce continuous in a couple of chapters' time. Now, the difference between discrete and continuous is kind of blurry. I guess there is a rule of thumb that exists in the world of maths where discrete probability or discrete events are considered countable. This means that you have individual specific outcomes that can be kind of pigeonholed into categories. So for the example of rolling a die, this is an example of a discrete event. Why is that? Because we know that there's only 6 possible outcomes, and it's definitely going to be one of 6 numbers. It'll be 1, 2, 3, 4, 5, or 6. Now, something that doesn't have that property is something like measuring heights of students. Now, that's why we use the colloquial term measurable to describe a continuous event. But let's take, for example, we measure all the heights of all the students in a classroom. I can't definitively say that there's going to be someone who has a height of 170 centimeters. I can't say there's definitely going to be someone who has the height of 180 centimeters. I don't know what the heights are going to be. So in that situation, we're going to use a continuous spectrum or a continuous model to define the heights of the students, because it's kind of blurry, the jump between different outcomes, i.e. in this case, different heights of different students. So in that case, it's much more easier and much more simpler to use a continuous model rather than a discrete model. I think once you get through some examples, it should become more and more obvious which one is which, and the question will give you hints about which one to use anyway. So let's continue with the discrete probability discussion with a very common example. I used it before as well. It's rolling a die. Now, we said before that the possible outcomes are 1, 2, 3, 4, 5, and 6. Now, they're all of the possible outcomes, and that's called the sample space. Now, sample space is denoted by this weird-looking E. It's a Greek letter. It's pronounced epsilon. Essentially, it's just a list of all the possible outcomes, and we put it into this squiggly bracket. So squiggly brackets in maths are generally used for lists. So this is a list. So that's a list. And then we've got the list of, obviously, the possible values. Now, the reason why we use a list rather than something that we've used for domain, such as set notation or interval notation, is because set and interval notation are continuous. However, if we want to describe individually 1, 2, 3, 4, 5, and 6 without connecting them, so for example, we don't want like 1.2, then we have to use a list format because that keeps the numbers or the objects in the lists separate. So that's why we use the squiggly brackets. Now, within this experiment of rolling a die, we have infinitely many events. We could create as many events as we like. Now, questions would usually suggest what the events would be, and it would usually have some sort of focus. So let's say we want to roll an even number, and we might define that as event A. Then A would obviously include the outcomes 2, 4, and 6. All the even numbers from the sample space. So that's this number, and this number. And you should see that all of the numbers in event A are from the sample space. And that's obviously because the sample space holds all of the values in this experiment. Event A, or any event for that matter, will always just be a subset of the sample space. Now, event B is rolling a number greater than 2, so that's obviously a different subset now. We just write down all the numbers greater than 2 from the sample space. So that'll be 3, 4, 5, and 6. Just chose true random arbitrary events from this experiment. Sweet. Now we have event A and event B, and now we can summarize this in a Venn diagram format. So we should be familiar about what a Venn diagram is and what it represents. So you can see that the left ring or the left circle represents event A. The right ring or the right circle represents event B. Now, where the two circles overlap is what's common in both. So let's start off with that first. We can see that 4 is included in both and 6 is included in both event A and B. So 4 and 6 will go here. Now, 2 will go here because it's in event A but not in event B. And then same thing for 3 and 5 on the right-hand side. It's included in event B but not included in event A. So that's why it has to be into the far right region. Now, you can see that 1 is not in either of these events, but it's still part of the sample space. So what we generally have to do, if you do further, then you might recognize that you will need a box around your Venn diagram to encapsulate the 1, which is going to be outside of the rings A and B, or outside of the events A and B. So I remember they were really picky on this when I was in maybe learning about probability and Venn diagrams in year 8, year 9, year 10. They said for Venn diagrams, you always needed a box around the Venn diagram, I guess, just the overall visual of it. So that allows for us to include numbers that aren't in the rings, but obviously are really important to the experiment because 1 is still a possible outcome. It's just not included in the events A or B. So this is a quick intro about probability. It should be more or less revision from what you've learned up until now, but still really important to know as we move forward when learning new things.